Part 9 of this series of talks about op-amps is about a couple of interesting little circuits which result when you put a capacitor in place of the resistor in an inverting amplifier. First circuit looks like this. Well, we can analyse this in the same way that we did the inverting summing amplifier. We just have to note the relationship between the current and the voltage across the capacitor. We can no longer just apply Ohm's law here. Well, capacitors have the characteristic that the charge on the plate of a capacitor is equal to the value of the capacitance times the voltage difference across the capacitor. That's the excess charge that's arrived on one of the plates. If we differentiate that with respect to time, we end up with the rate of change of the charge on one of the plates of the capacitor, but that's just equal to the current. That's the current flowing onto the capacitor. So the current flowing onto the capacitor is C times the rate of change of the voltage across the capacitor. Apart from that, this works just the same as an inverting amplifier. So once again, we can assume that the inverting input here is a virtual ground and is at 0 volts, the same potential as the non-inverting input. And once again, we can apply Kirchhoff's current law to this node here, and note that the current flowing in is now I times C times D by dt of the voltage across this capacitor, which is the voltage at A minus 0, because this is a virtual ground point. That's just C dA dt. The current flowing out of this node must equal the current flowing into this node, so the current flowing through that resistor there, that 1K feedback resistor, is also C dA dt. That means the voltage across this feedback resistor, which is the voltage here, which is 0, minus the voltage here, which is V out, must be equal to the current flowing through this resistor in this direction, which is C times dA dt, times the value of the feedback resistor, which in this case is 1K, but in general I could just call RF, the value of that feedback resistor. That gives me that V out equals minus C RF dA dt. We have an output here which is proportional to the rate of change of the input, otherwise known as a differentiator. The output is proportional to the differential of the input. If the input is not changing very much or changing very slowly, we will get a very small output. If the input starts changing very quickly, then we'll get a larger output. We could also put the capacitor in the feedback path, and we'd end up with a circuit like this. The analysis is very similar. The current flowing through this input resistor here, I'll call it Rin, 1K in this example, would just be A minus 0, because this is a virtual ground point, the same. A minus 0 divided by Rin. Rin being this input 1K resistor at the moment. Therefore, the current flowing out through this capacitor. Well, I say current flowing through the capacitor. Effectively, the charge is arriving on this plate of the capacitor, and an exactly equal amount of charge is leaving the other plate of the capacitor, but charge doesn't actually flow through the capacitor. That's why it has this circuit symbol with a gap in between. But anyway, the current flowing into this capacitor and out of this capacitor must be equal to this. And we know that for a capacitor, this current is equal to C times dV dt, where V is the voltage across the capacitor. In this case, V is 0 minus V out. So that would be C d by dt of 0 minus V out. And that is just C times minus dV out dt. And this current must be equal to this, A over R in, which gives us that dV out equals minus C times R in minus 1 times A, more usually written, minus A over C R in. So now we have a situation in which the differential of the output is equal to the input. In other words, the output is proportional to the integral of the input. And it's known as an integrator. I should point out, of course, that if you actually built this circuit, as it's drawn here, it will not integrate the input, because there is no feedback path at DC. If you can just consider very low frequencies, the capacitor has no effect at all, and the output of the op-amp would therefore saturate, because there's no negative feedback pulling it down. So what we tend to do when we're building these things for real is we put a, sometimes called a leakage resistor, across the capacitor like that, of a large value, and its function is to stabilize the output at DC, so the output doesn't automatically saturate. And this sometimes also known as a leaky integrator. Later on in the course, we'll be looking at how to combine diodes into op-amp circuits as well, and produce circuits which can not only add and subtract and integrate and differentiate, but which can take logs and multiply and divide two voltages as well. There's a whole world of analog computing you can do with op-amps, diodes, capacitors, resistors, and a good knowledge of basic op-amp theory. That's all I'll be saying for now about ideal op-amps and linear circuits. In the next videos, we'll be looking at non-linear op-amp circuits, those with diodes in them, and the effect of the imperfections of real op-amps on circuit performance.